Hello, everyone, and welcome to my channel. This channel is an educational channel, and we try to take deep dives into great theories of everything that you probably never heard of before, all-encompassing theories and paradigm shifters that you can employ in your life to enhance your experience. And today is the 434th video that we've done on Dewey B. Larson and his reciprocal system of theory. Mr. Larson proposed his two fundamental postulates in 1959 about how the universe operated. And then he took those postulates and through a process of deduction, he arrived at a theoretical universe, what his universe would look like if his postulates were correct. And then he wrote a lot of books, and many of them compared his theoretical universe with the actual observed universe of the scientists that they had compiled through laboratory and observatory experiments. And we are looking at one of his books on chemistry called Basic Properties of Matter. And Larson theoretically derives equations for many of the basic properties of matter, such as the melting point and the compressibility and the specific heat and the interatomic distance. And then he compares his results with those of the scientists. We're looking at chapter 4 of his book called Compressibility. And we're right in the middle of that chapter. We're moving real slow. Because it's a real slow read and it's pretty difficult material, but the point is that you don't get bogged down. Just keep moving forward. If you don't understand something, just move on. You probably will figure it out later on. You know, we're really just trying to get the basics and then kind of see how he applies it. There's a lot of weeds, a lot of details that are not quite relevant for a beginner, but he puts them in there. And so you just let them wash over you, and you pretty much say, you know, I'm obviously going to have to read this book again. I'll pick it up the next time I go through. I'm just trying to get the big picture here. But I want to also let Larson speak. So I like to read his books into the record because I don't feel competent myself to interpret what he's writing. I'm struggling to understand it too, even though I've read these books a number of different times. Every time I go through them, I get more out of them, but you know, I still haven't, you know, I'm still not capable of acing any kind of test, or, you know, I'm happy if I can, you know, make a little bit of progress from one to the other. But the thing that you have to really keep in mind is that Larson's reciprocal system, it's a system of theory. It's a general theory. And so if you learn how he does it in one subject, then you can apply it to other subjects. It's not like legacy science where every subject is compartmentalized and you have to learn an entire new discipline to you know, to enter into any new subject. You know, you can't, you know, study biology and use what you've learned in biology in astronomy. And you can't use what you've learned in astronomy in geology. But with Larson, you learn one, you know, one system, one, you know, general way of going about it, and then you can apply it to any subject. So, you know, it's not quite an equivalence there. So don't get discouraged if you don't really get it. You know, you'll pick it up, but you will see eventually that Larson uses the same approach for all subjects. I mean, there are some differences, but in general, he's using the same approach. Okay, now what is the reciprocal system? It's called the reciprocal system, also called the universe of motion. Larson constructs a universe not based on matter, not based on energy, not based on the four fundamental forces, but Larson bases his universe entirely on motion. And in particular, he's referring to a kind of motion that is called scalar motion. A scalar motion is a motion that has a magnitude but has no specific direction. So this is a more generalized kind of motion, non-localized kind of motion. You can envision a scalar motion if you take a balloon and you put some dots on it, some spots on it, and then you blow up the balloon. All of the spots will be moving away from each other. But they won't be moving in any specific direction. Every dot will be moving away from every other dot. And the same will be true if you contract the balloon. Every dot will be moving toward every other dot. And you could have the temptation to abstract that whole picture and arbitrarily assign one of those dots as being motionless. Then you could start imputing directions. Then you could, and you could also impute a force field if you're talking about that inward contracting motion. All of the dots will appear to be moving toward that one dot that you have assigned as motionless. It'll appear as if there's a force field kind of emanating from that one dot that's motionless, and that all the other dots are in this force field. But that is not the case. The force field and the directions are strictly the result of the reference point that you've assigned, not the motion itself. The motion itself has no direction, and there is no force field. All of the dots are moving toward or away from all of the other dots. So with a scalar motion, the only direction you have is in or out. And the outward motion Larson calls the progression. The inward motion Larson calls gravitation. And another aspect of Larson's reciprocal system, where you get the reciprocal name, is that motion, because other people have tried to construct a universe of motion before, but have failed. They haven't, first of all, acknowledged any type of scalar motion. But then they've also not been able to redefine motion or define it more specifically as Larson did. Larson defines motion as the relationship between space and time. So in motion, space and time are the two reciprocal aspects. Now just try to, before you think how absurd it is to say that time is the reciprocal of space, think about the most basic kind of motion that you can think of, speed. The bicycle is moving 10 miles per hour. 10 miles of space in 1 hour of time. Space over time is speed. Now, double the speed. You can now say the bike is now moving 20 miles per hour. But you can also say the bike is now moving 10 miles per half hour. You can either multiply the space or you can divide the time. That is a reciprocal relationship between space and time. But Larson generalizes it beyond just speed and applies this principle to all forms of scientific phenomena. He defines them all as motions. So not just speed, not just acceleration, but also to matter, energy, force, electric and magnetic charges, and many of electric and magnetic phenomena such as permeability, permittivity, magnetic flux, electrical capacitance, also surface tension and viscosity, power. These are all fractions. with space or time as the numerator and time or space as the denominator. Now, space or time and motion come in up to three dimensions. So you can have, like for matter in Larson's system, matter is time to the third power over space to the third power. So, you have all of those different permutations of fractions of space, space as the numerator, space or time as the numerator, and time or space as the denominator. So when you have the three dimensions of space, that's generally what we observe in the universe, in our environment in the universe. We observe three dimensions of space in a still frame, what he calls the spatial reference system or coordinate space. And we are moving through time. Things are unfolding in time. Time is getting later and later and later. So what we're really seeing is we're seeing three dimensions of vectorial motion or vectorial space, really like an abstraction. We are anchored to that spatial reference system. So we see space as being still, and we see the three-dimensionality of it. But we see time as a scalar phenomenon. Time is getting later and later and later, but in no specific direction. Now, there is another environment in the universe where you would see the reciprocal of that. You would see three dimensions of time in a still frame, and you would see space progressing, space always getting farther and farther and farther apart, like on the surface of an expanding balloon. And that comes about basically through this discrete unit postulate, which is another aspect of Larson's system, which his fundamental postulates: space, time, and motion come only in discrete units. They are quantized. You have to have a full unit of space before you have space. You have to have a full unit of time before you have time. And if you have exactly 1 unit of space in 1 unit of time, space over time being speed, then you have what Larson calls unit speed. 1 over 1 equals 1. And unit speed is also known as the speed of light. So in Larson's system, he has what you would call a 0-point motion, or a null point, or a reference point. He calls it the progression of the natural reference system. That is a motion outward at the speed of light in all directions. That is the empty universe of Larson's system. This is the universe with nothing. This is a universe of nothing. And this is not perceivable by us, but it is a motion moving outward at the speed of light in all directions. This is the 0 point of Larson's universe. And he takes his measurements from that point, whereas legacy scientists take their measurements from zero motion, from that spatial reference 0. Larson calls that the conventional reference system, but he takes his from the natural reference system, the reference system that nature actually goes by, which is outward in all directions at the speed of light. So what this also means is that there is a half of the universe that's moving faster than the speed of light, and half of the universe is moving slower than the speed of light. The half that's moving slower, he calls the material sector, and this is the sector that we're familiar with, and it has the relations of coordinate space, 3 dimensions of space in a still frame, and clock time. Clock time is always progressing, getting later and later and later. But if you go into the cosmic sector, you cross that boundary of the speed of light, or unit speed, and you move into the cosmic sector where everything is faster than light. Then you have coordinate time, 3 dimensions of time in a still frame, and you have clock space. Space is always getting farther and farther and farther apart. And so in this cosmic sector, you have basically cosmic atoms and cosmic particles, cosmic molecules. In the material sector, you have material atoms and material particles. And those both form in the inside regions of both of those sectors. So within the material sector, there's an inside region that Larson calls the time region. And again, this is from the discrete unit postulate. If you don't have a full unit of space, such as two atoms interacting in a small space, if you don't have a full unit of space, then you don't have space. And if you don't have space, then you only have time, because the universe is made out of space and time, motion. And so Larson calls that the time region. And that's the region of atomic and molecular interactions. And again, when you cross that unit space boundary, you reverse the rules. And now the progression is moving inward and gravitation is moving outward. And the same is true in the cosmic sector. If you go in less than 1 unit of time, then you have what Larson calls the space region. And in the space region, that is the region of interaction of cosmic atoms and cosmic molecules, which we know of as antimatter or mesons. And then matter is really formed out of the progression, the source, out of the progression of the natural reference system. That is really the source of matter. But matter comes by basically reversing that motion. So you have to more or less rotate that motion in 3 dimensions. And then you end up with atoms. And so in Larson's system, atoms are notated with 3 numbers. The first is a 2-dimensional rotation, primary, and the second is a 2-dimensional secondary motion, and they alternate. And then the third number is a 1-dimensional rotation in the opposite direction that is optional, meaning it can be 0. In the noble gases, it's 0. And it can be positive or negative, whereas the first number has to be positive. The first 2 numbers have to be positive. And so Larson starts with that, and then through a process of deduction, he derives his equations for the basic properties of matter, including the compressibility that we're working on this chapter. Basically, Larson will say that the pressure is related to both the internal pressure and the external pressure. So the internal pressure comes from the progression, because the progression is moving everything inward in time. So this is an internal or already existing pressure, because the progression is omnipresent and eternal. It's always existing. So it's always there, and it has to be factored in. And then in addition to that, there can be an external pressure. And so you have to add them both together. And what compression does is it reduces the volume of the matter, of the atom or the molecule. And so what you do is you basically take the relative pressures. You measure the pressure like under 1 atmosphere, and then then you measure the pressure under a different pressure, and you compare them, and that helps you. And then if you take the derivative of that, then you end up with the compressibility, the rate of compression. So he calculates all of these things in this chapter, and he's about to, I think, arrive at a new one, but we'll just get started. And There'll probably be many places where you get confused if you're not already, but I would suggest just trying to hold on and listen in and pick up what you can pick up, and put it in your memory bank for later. Okay, because of the nature of this compression pattern, a convenient method of analyzing the experimental values of the volume of various substances under compression can be made available by expressing that previous equation in the form of V sub 0, or the initial volume, over V to the second power equals 1 plus P over the initial pressure. I believe it might be compressibility. Now, that second power relation that's there, that second power, is because of what he calls equivalent space. When you look into the time region, we are anchored to the spatial reference system. So we don't see time, we only see space. It's arguable that maybe we hear time, but we do not see time, we only see space. And what we see when we look into the time region is we see what he calls equivalent space. We see the time equivalent of space. So we see the inverse of the time. And because time and space are reciprocals of each other, but it is reduced, we see only a fraction of that. He calls that the interatomic distance. That's what's lost in the translation when you're looking into a different sector or a different region of the universe. But also you reduce it because equivalent space is a second power relation. And so, and that comes about algebraically because when you're talking about speed, space equals 1 over time, and then you have to put that over time as well, because space over time is motion. So when you're looking at motion at space over time, that becomes 1 over time to the second power. So that is, the time that you're seeing is a second power relation. So that's why this second power thing is in this volume equation. Okay, I think he's going to explain this equation here. According to this equation, if we plot the reciprocals of the squares of the relative volumes against the corresponding total pressure ratios, we should obtain a straight line intersecting the zero pressure ordinate at the reference volume 1. Okay, so let me just read that sentence again, and maybe you just try to visualize it, put your little graph up in your head and see. Okay, according to this equation, if we plot the reciprocals of the squares of the relative volumes against the corresponding total pressure ratios. Okay, we got two volumes here. One is the original volume and one is the volume under this pressure. And we take their fraction, but it's at the second power. So plot the reciprocals of the squares of the relative volumes against the corresponding total pressure ratios. So again, the original pressure and the experimental pressure, or what we call. We should obtain a straight line intersecting the zero pressure ordinate at the reference volume 1. So when the pressure is 0, the volume is 1. The slope of the line is determined by the magnitude of the internal pressure, P sub 0. And he does have a figure here in the book that shows this curve. So I don't have access to that here, but figure 1a is a curve of this kind for the element tin based on Bridgman's experimental values. Where there is a transition to a higher set of compression factors, and these compression factors come into play, they are derived from the three-number system that Larson uses for the periodic table, and they can be they are activated. More of them are activated the higher the pressure goes, and they're based on a cross section because the pressure, the compression is two-dimensional and the volume is three-dimensional. So there is an orientation of that volume to basically there's only two dimensions that are subject to this pressure out of the three. So depending on how strong the pressure is, that determines how many of these compression factors are activated. He explained this several days ago while we were going through this. Okay, so where there is a transition to a higher set of compression factors within the experimental range and the magnitude of P sub 0 changes, the volumes diverge from the original line and follow a second straight line, the shape of which is determined by the new compression factors. I'm preparing curves of this kind for the other elements investigated by Bridgman. We find that about 2/3 of them actually do conform to a single straight line up to the 30,000 kilogram per centimeter squared pressure limit of his earlier work. I think that is approximately 30,000 atmospheres. So that was the limit that Bridgman, and Bridgman, he was early 20th century, so, we're going pretty far back, and the limit of his study was about 30,000 atmospheres. Nowadays, or even in the days that Larson wrote this in the 80s, they went much higher. Those pressure limits went much higher. His studies of the less compressible substances, such as the higher elements of the electropositive divisions, were not carried beyond this level, but he measured the compression up to 100,000 kilograms per square centimeter on many other elements, and most of them were found to undergo a transition in which the effective internal pressure increases without any volume discontinuity. The compression curve for such a substance consists of two straight line segments connected by a smooth transition curve, as in figure 1b, which represents Bridgman's values for silicon. So that actually tends to be a pattern that happens also with the specific heat curves that we'll look at in the next chapter or the one after, where you don't have a straight line curve. You have segments at different kind of inflection points. The kind of the new compression factors kick in, and so the slope of the line changes. So it's not a straight line, it's several straight line segments. And he says here that they are connected by a curved, what does he say? Two straight line segments connected by a smooth transition curve. I'm not sure why that transition curve would be smooth, but maybe he'll get to that. Okay. In addition to the changes of this type, commonly called second-order transitions, some solid substances undergo first-order transitions in which there is a modification of the crystal structure and a volume discontinuity at the transition point. So not only are the more compression factors being activated, which causes a bend in the curve, but then there is also a modification of the crystal structure, really the atomic configuration. Remember, in Larson's system, atoms are not in contact in the solid state. In Larson's system, atoms are the nucleus. Okay, in the legacy science, there's a nucleus, and then there's this big electron cloud surrounding it that is much, much, much bigger than the nucleus. In Larson's system, there is no nucleus. There is only the atom. The atom is the whole nucleus, and the distance between the atoms is what he calls the interatomic distance. So there is a distance between atoms in Larson's system, whereas there really isn't in the legacy science system. So that basically creates this crystal structure, and it can alter depending upon different elements have different forms of bonding with each other, with each other's atoms, and there can be a transition of the crystal structure as well as this increasing the compression factors. Now, once again, you can think of this as kind of like a fudge factor that Larson is employing all of these different methods to make his data conform to Bridgman's experimental results. And that's, I think, a valid criticism, but I think if you pay attention to what Larson's doing, he does it consistently, not only just in chemistry, but in other subjects as well. And so he uses the same kind of principles throughout. And I think that you can see that he's not fudging his numbers to be in line with the experimental data. And I also think that even if he was, it wouldn't be successful, because these numbers that he's adjusting, they wouldn't necessarily put him within 1% of the theoretical the experimental values. I think these are more kind of gross changes that he's advocating here, or that he's saying that occur. Either way, thanks for tuning in.